All right, today we're going to talk about nuclear chemistry. We've talked about a lot of things up to this point. We're going to pull some of those things together for this unit, focusing primarily on what is it and what are some practical uses we can actually use nuclear chemistry for. Now, before we can do that, we have to have a quick review to make sure we understand a few really important pieces before we jump into the more specific details of nuclear chemistry. So the first thing we have to talk about is isotopes. We've talked about these. Now we have to recall exactly what these things are. So isotopes are atoms of the same element that have different numbers of neutrons, all right, and different mass numbers. So because they have a different number of neutrons, their mass number has to change as well, because as you remember, when we're looking at an atom, the two things that contribute to the mass of the atom is going to be the protons and is going to be the neutrons. So again, mass number is the mass of an individual isotope of an element. So because the numbers of neutrons in the isotopes of an element are different, the mass numbers are also different. Okay, and so that's the idea that we have here, in which we have neutrons changing. So you can see we go from 6, 7, and 8. Protons are the same in this scenario, all right, because protons, if they change, they actually change the actual identity of it. And so these are still all carbon, they're just different versions of it. So there's carbon 12, carbon 13, and carbon 14. Because of your different versions, that allows us to get something called carbon dating, which we'll talk about later. The next thing we need to talk about is, more specifically, the atomic mass. Remember, this is not the mass number. Atomic mass is different. Atomic mass, because most elements have more than one isotope, each element is given an average mass. That's the atomic mass. All right, remember, mass number is the mass of that specific individual atom. Atomic mass is essentially that average. So the atomic mass of an element is the average mass of the mixture of its isotopes. So for example, if 4 out of 5 boron atoms are boron 11, therefore 1 out of 5 are boron 10. So we add all those things up, gives us 54. 54 divided by 5 is going to give us 10.8, and we'll see if you look up boron, it'll typically be 10.8, and in this case we just have a few more decimals, which makes us happy. Still stuck? Ask me in class and we can help clarify those issues, because if we don't understand those things, these next few things will be difficult. Alright, so now that we have that little review covered, we have a better understanding of what we're getting into, let's actually talk about what nuclear chemistry is. Nuclear chemistry is the subdiscipline of chemistry that is concerned with changes in the nucleus of elements, hence nuclear chemistry. These changes are the source of radioactivity and nuclear power. And so we've talked about radioactivity a little bit when we talked about electromagnetic waves, and you may be familiar with nuclear power if you think of a nuclear power plant or the sun or all those things. So what is radiation? Well, radiation is energy traveling through space in the form of electromagnetic waves. You may remember electromagnetic waves from our waves unit. And here's just kind of a little reminder as well, in which we have this radiation spectrum, in which we have, you know, our side here and our side here, in which we have our wavelengths getting from really long to really short, and same with our frequency kind of changing. And of course, there's just this little bit here is what we actually can see, even though there's a whole bunch of other things going on. So building off of this, what's radioactive decay? Well, radioactive decay is the spontaneous breakdown of an atomic nucleus resulting in the release of energy and matter from the nucleus. So if we have some sort of atom that's considered radioactive, energy can leave it, and then what ends up also happening is generally there's some form of particle that also leaves. Because the particle leaves, there's energy released, which is radiation. And we'll talk about why does this specifically need to happen. Alright, So let's I'm going to throw a huge wall of information at you here, and we'll talk about it. So there's three main types of radiation. There's alpha, beta, and gamma. Alpha is the nucleus attempts to find stability by emitting an alpha particle. It's identical to a helium nucleus, 2 protons and 2 neutrons. So sometimes we'll say in alpha radiation we lose a helium. Now that's not technically correct, but the amount that we lose is equivalent to a helium and can also oftentimes be abbreviated as such, and which we'll see in a few of our examples. Beta radiation, or sometimes referred to as beta decay, involves the transformation of a neutron into a proton. That's super important, this idea of it turning into a proton, through the emission of an electron. So an electron gets kicked out, and this actually causes a neutron to change to a proton in this scenario. Now, gamma decay, or gamma radiation, is a loss of energy by the nucleus, much like an emission of light or X-rays. This type of radiation is usually instant and helps stabilize the energy of the atom. Typically, when any of these things happen, there's some form of instability, and they're trying to, become happy. Remember, we've always can use that expression, which all atoms want to be happy, and so they don't like to be at these different energy levels. So, as the previous two types of decay involve an increase in nucleus energy, gamma rays almost always follow the emission of an alpha or beta particle. Essentially, gamma rays come after either an alpha or beta emission, but not before. Typically, gamma radiation just doesn't happen. There is some alpha and some beta that also occurred. All right, so these attempt to find stability, okay, energy levels get thrown off, which generally leads to gamma radiation. And we'll look at some examples of where this could occur. So let's look specifically at this alpha. And again, I've kind of been calling it alpha radiation and alpha decay, and those can kind of be used interchangeably. Alpha decay is specifically looking at how are things changing. So here, alpha decay results in the loss of 2 neutrons and 2 protons. Okay, that's what we said just on the last page. This means the atomic mass decreases by 4, again, 2 protons plus 2 neutrons, and the charge decreases by 2, loss of 2 protons. All right? And those are positive, so losing 2 positive things will bring our charge down. So our example here is, remember, so we have our atomic mass and we have our atomic number. That's what these are. We have what happens, so then this goes through alpha decay. And so these signs, just like any of our past chemical reactions, have to be balanced, which means you'll notice this 222 is 4 less than this 226. Where did that amount go? It went here. Remember how I said we can represent that with helium, because that's the amount that's lost, and so that's kind of this helium piece. And then we have our 88 here for our atomic number, which now becomes 86. So now we have an actual different element that has occurred due to this decay. It's changed. Alright, so let's talk beta decay. So beta decay results in the gaining of a proton as a result of a neutron losing an electron. So let's talk about this piece right here. That can be confusing because you may read them like, well, hold on, how can a neutron lose an electron? That sounds weird. And it is. Now, we don't go into the full detail of actually what is going on. We get into things called quarks and all these crazy things. The idea essentially being is a neutron loses a small piece of a negative particle. That's a part of it. That losing of a negative particle gives it a positive charge, making it a proton. Okay, so essentially a neutron is made up of these other really small subatomic parts, generally called quarks, and there's a loss of a negative particle in beta decay, which then makes it more positive, which essentially, as a net, turns it into a proton. Okay, and I know that sounds kind of confusing. But stick with me. So because electrons have almost zero mass, so just as a reminder, that's 1 of 840 AMU, right? We make the assumption it has no effect on the atomic mass. So that doesn't change when we lose that negative particle. The charge increases by 1 as we lost an electron. More specifically, we lost this negative thing. More importantly, we gained a positive charge. So the atomic number increases as there is a gained proton. So we lost this negative piece. Now what I also want to highlight is this electron we are losing is not an electron we are losing as in like an orbital, right? So we've talked about electrons bonding, or they can have charges and ions and these electrons in the orbits. That's not where this electron is originating. This electron is originating from the nucleus as a small subatomic particle. Okay? There's a negative charge, so we call it an electron. So we gain this proton, but we've done nothing to our mass. We just changed one of our pieces from being at essentially 0 charge to a plus charge. So if we look at our example, we have our carbon 14, maybe 14. We have nitrogen, which is going to have 14, but now we also have our number here of 7. Okay, so our atomic number has changed as a result of this. Remember we said, oh, they want to be balanced, and that's true. We have this -1 here. This is 7. 7 minus 1 is 6. Okay? Beta decay is typically the hardest one to wrap your mind around because it has the most abstract thought. And we don't go into the extreme detail of explaining exactly how it is going. If you want to know more, ask me in class and I can point some resources in your way if you want to investigate in it further. In general, the idea you need to know is in beta decay, the atomic number is the only thing that changes because a neutron essentially gains a positive charge, turning into a proton as a result of a loss of a negative thing, which is our electron. Okay? All right, our last one for types of radiation or decay is going to be gamma, and we get this fun little loopy Y symbol here, which is gamma. Gamma never changes the charge or the mass. However, it frequently goes hand in hand with other forms of decay, meaning there is a gamma decay, alpha and beta, or meaning where there is gamma decay, alpha and beta are sure to be there as well. So typically, gamma decay is kind of like this, I always thought of it as a fail-safe mechanism, where we have this alpha and beta, which are these attempts to stabilize, and then gamma kind of has to step in when things go critical and just release a whole bunch of energy. And that's why you think of gamma radiation as being very harmful, and that's true, because it's really, really high energy. All right, I want you to stop here and work on the first few pages of your workbook that deal with radioactive decay. Once you finish those or feel well enough with them, you can continue on with this video and complete some of the notes. The next piece we're going to talk about here is nuclear fission and fusion. So you may already know some things about them. So fission is the splitting of a large atom into 2 or more smaller ones. Does not normally occur in nature. Produces highly radioactive particles. Requires relatively little energy to split 2 atoms. And it's the type of reaction that is used in atomic bombs. Okay. Fusion is the fusing of 2 or more lighter atoms into a larger one. This occurs in stars such as the sun. Less radioactive particles, when we compare it to fusion, requires extremely high density and temperature to actually occur, And this is actually how some hydrogen bombs function, or how hydrogen bombs function. And that's why, if you look those things up, hydrogen bombs are substantially more powerful than atomic bombs. So a nice little graphic here that I can show you is we have fission, which is we have a larger particle splitting into two smaller particles, or we have fusion, two small particles fusing into one larger particle. Remember, fusion requires a lot more energy and produces a lot more if it's done in the way of a hydrogen bomb. So this brings us to something called a half-life. Now, you may have heard of this before. A lot of times it could be called carbon dating, because sometimes we can use carbon for measuring the age of really, really old things, because it has a really long half-life. And we can use it for a lot of other things. It can actually affect like the shelf life of some medicines and all this. So let's talk about what half-life is. So half-life is the radioactive half-life for any given radioisotope. It is a measure of the tendency of the nucleus to decay or disintegrate, and as such is based purely upon that probability. So essentially what this means is it is the amount of time for half of the stuff, right, half of whatever it is, and the atom to decay, hence half-life. So it's how much time goes by for half of it to be decayed into something else. Think of, you know, if you have a banana and it's sitting out and rotting, how much time would it take for half of it to be all rotted? Then that may be the half-life of a banana, okay? Okay, so how do we calculate it? Well, we have a very complicated looking equation. I know, it's scary. Don't worry, I color-coded it. And it'll make sense. Alright, I promise, it's not as bad as it looks. Our initial activity is this capital A with this little 0 here. This, we put on a lot of variables you may see in your future. It indicates the initial of something. So it stands for initial, and activity here is going to be what, in our case, we're going to use mass. So how much of it we have. Our E here is a constant, always going to be the same number, 2.718. So you'll always have this provided for you. Okay? This is just part of the equation. That's another constant. Now we just put in the equation. Make sure when you enter this into a calculator, this is negative. Alright? So don't forget that negative, or you'll find yourself getting incorrect answers all over the place. And we don't want that. This lowercase t, time since initial activity. So basically what that means is how much time has passed since we had it from the beginning point to the point we have it now. It could be 3 days, it could be 5 years. And then we have our t, and then subscript half. This isn't actually part of that equation. This is a whole representation saying half-life of the element. Alright, so if the half-life is 10 days, we put 10 days. If it's 20 minutes, we put 20 minutes. Okay? That's the idea. One final thing I will mention when it comes to this is that these, so this T and this T, since we're being divided, we don't want to have units on our power, have to be in the same unit. Meaning, if our half-life is given to us in days, we have to have our initial time in days. So if we aren't given it in time, we have to convert it. Okay, so always make sure these are equivalent units so they cancel out. Or again, you'll find yourself getting some weird answers. Alright, so if we look at an example, if there is 100 grams of carbon, 14 in the Earth, after 8,000 years, how much will be left if the half-life of C14 is 5,730 years? So that's a long half-life. That's why we use carbon for dating things. We can see how much of it remains of that particular isotope, and it can tell us how old it is very accurately. That's how, if you ever wondered, oh, we know that this is 3,000 years old, and you wonder, how do we know that? Carbon dating, typically. So, We identify our variables, so our A sub 0, our initial activity here, we had 100 grams. Okay, our T, our initial time, basically how much time has passed, is 8,000 years. Alright, our half-life, we were told to be 5,730 years. So we're nice and we have both of those in years. We don't have to do any converting. And E is always given to us at 2.178. Okay. So if you did the math, then we have 100 times this 2.718 to the power of this 0.693 times 8,000 years. So we'll have all that divided by this 5,730 years. Sorry, I kind of got cut off here. Which meaning A, if you did it correctly, made sure you got all punch in, is 38 grams of carbon-14 will be remaining. Essentially, 38% will be left. Which is pretty cool to be able to figure out.